Hello everyone and welcome back to Networks class. Last time in class we discussed an overview of the different kinds of network models. So in particular you saw 4 different kinds of network models and one hybrid model. And the reason we discussed that is because very soon I'll be asking you to think about which of those models applies to your particular real-world situation. So very soon you have to take the CSV files you created for your project and actually solve a optimization problem to see how well the network for your project actually performs using one of these network models. So the plan for today is to talk about a new problem called shortest path interdiction. So the basic idea behind this problem is that somebody else is solving a shortest path, and what we'd like to do is go in and make their life as difficult as possible. So we want to make their life we want to make their shortest path to be as long as possible by doing things like maybe lengthening some edges or getting rid of some edges entirely. So let's just jump in and discuss the shortest path interdiction problem. So first, recall what the shortest path LP looked like. It looked something like this. So we had to minimize over the y the sum of Cij times Yij, subject to some network flow constraints, and the y's had to be bigger than or equal to 0. And now suppose that somebody else has a problem like this to solve, so they're trying to minimize the shortest path. And what we want to do is make that bad for them. So we want to maximize. So we have some kind of x variables. Let's say that there's one for each edge. So on each edge, we'll have a decision 0, 1 that says, do we attack the edge or not? And if we attack the edge, what that's going to do is maybe lengthen it or get rid of the edge entirely. And if we don't attack it, then the person over here who's is trying to solve the shortest path is going to experience the Cij edges, edge lengths, whatever those original edge lengths happen to be. But if we do attack it, then we might kind of bump up these edge lengths. So what we're going to do is we're going to replace these original edge lengths. We're going to replace them with something like Cij plus Dij times Xij. So you can see that if the Xij here is 0, you get back the original Cij. And if the Xij is 1, then you get a lengthening over here. So this Dij, you can think of this as meaning how effective an attack on edge ij is. So if the Dij is something like infinity, it means that we have a very effective attack because after we do the attack, the edge is essentially unusable. But the attack might just kind of lengthen this edge. So whereas originally maybe it took half an hour to cross the edge, now it maybe takes 45 minutes because we made it slightly more difficult to go across there, but the person could still possibly go across that edge. So that's the basic idea of how our attack decision variables influence the graph. But another thing that might happen is that we might not be totally unrestricted in how we attack. So for example, we might have a constraint like this, that the xij's, the sum of the xij is less than or equal to 5. So a constraint like that would be telling us that you cannot attack more than 5 edges. Or in general, we can express this as just the x variables have to be in some kind of constraint set. So these are resource constraints on the attacker. So let's just clean this up a little bit. Clean up our thought process and rewrite it a bit. So we have something that looks like this. So maximize over some x variables, minimize over some y variables, the sum of Cij plus Dij Xij, subject to some kind of network flow constraints on the y variables. The y variables have to be bigger than or equal to 0. And then we also have some resource constraints on the x variables. So that's the basic idea of us attacking, but let's be very exact on what this means. So the meaning over here is that you can think of this as a game between two players. So there's an attacker, and the attacker is kind of like the x variables, versus a defender, or oftentimes the defender is called the operator. So the operator is this person who's actually trying to solve the shortest path. And the operator, you can think of that as the y variables. And the game is a sequential game. So first, the attacker chooses where to attack. And then the operator observes the results of the attack and adjusts to the best of his ability. So that's what's going on here. In particular, I want to be very clear that this is kind of a sequential game where all the information is available. So the attacker chooses where to attack, and then the operator sees exactly where that happened, and then knowing where those attacks happened, they adjust operations as best they can using the resulting network. So there isn't any kind of hidden information or simultaneous play going on here. It's just sequential. So that's the basic idea of the mathematical model that we wrote up here. And it's quite a reasonable game to think about. But computationally, there's a number of things that are worrying us about the particular mathematical formulation that we wrote up here. So the couple of things that are worrying us are the following. So first, over here, we're multiplying two decision variables, which means that this is a not a linear program, which make things, of course, very hard to solve. But another thing that's also worrying us a lot is the fact that this program actually has two optimization operators. So some of the variables are trying to maximize, while others of the variables are trying to minimize. And there really isn't a solver. So Cplex or a modeling language like GAMS, those things cannot really take in problems where some of the variables are trying to maximize, other of the variables are trying to minimize. And so currently, as we've written it, we have no way of solving this problem. But let's try to brainstorm a couple of ways to try to get around this. Okay, so this was our original formulation. So let's, in terms of these two problems, let's just consider this two operators problem first. And then we'll worry about this multiplication one later. So for these two operators problem, if somehow we could take this inner minimization problem and turn it into a maximization problem, that would kind of solve our issue. And generally, there are two ways of doing this. One way of turning a minimization to a maximization is to switch the order with some kind of -1. So if you somehow multiply by a -1, that's going to switch a max to a min. And another way of doing this is by taking a dual. So let's first try out what happens if we do this -1 trick. So let's multiply by 1 in here. And if we take this -1 inside the minimum, that's going to get changed to a max. But the problem is that this second -1 is still going to stay here. So what we'll have now is two sets of variables, the x and the y's. And they'll both be trying to maximize, but they're going to have different objective functions. So one set of the variables is going to have an objective function that's a negative of the other set of variables. So that doesn't really solve the problem. So let's instead try to take the dual of this inner problem. And when we take the dual, we're going to end up with something that's a max in there. So let's see how that works by being pretty careful about just taking the dual of a shortest path problem. So a shortest path problem just looks like this. Minimize over y, sum Cij, Yij, subject to all of our network flow constraints. And the y is being bigger than or equal to 0. So this is just the shortest path problem. So let's introduce some dual variables. So there's going to be one dual variable for each constraint. So we're going to have a dual variable associated with this constraint that we'll call pi s, with this constraint that we'll call pi t. And with all of these other constraints, we're going to have a pi a. So these constraints, remember, are for all nodes not equal to s and not equal to t. So let's write down what the dual looks like. So since the primal is a minimization, the dual is going to be a maximization because it has to be the opposite. And of course, this maximization is going to be over these dual variables. So we're going to maximize over the pi's. And the objective function here is just going to be the right-hand side times the dual variables. So that means I get a minus pi s plus a pi t. So that just came from this -1 times the pi s plus this 1 times the pi t. So let's now figure out what the constraints of the dual should be. So there's one constraint for each of the primal variables. And the right-hand side of the constraint is just the coefficient of the primal variable over here. So on the right-hand side here, we're just going to have a Cij. Let's for a second leave blank what the inequality operator is, and let's figure out what's on the left-hand side. So this particular variable Yij comes from one edge that goes between nodes I and j. And so this variable Yij, you can think of it as y Seattle to New York. This variable is going to appear in exactly two of all of these constraints. It's going to appear in the constraint for I, and it's going to appear in the constraint for j. So in the constraint for I, it appears with a -1 coefficient because it's leaving node I. Because it appears with a -1 coefficient in that constraint, which has a dual variable pi I. Over here, we're going to have a minus pi I. So that comes from the -1 coefficient of the y for this constraint for node I. So similarly, the Yij is going into node j. So here, we're going to have a plus pi j. And that again comes from the +1 coefficient of the y into the constraint for node j. And then for the inequality here, you can just look at the dual cheat sheet that we passed out in class. We're going from a minimization problem to a maximization problem, and the original variables were bigger than or equal to 0. So that means that the resulting constraints have to be a less than or equal to. So that's how we just get a less than or equal to over there. So that's our dual. And of course, these pi variables here are unrestricted. And that's because the pi variables corresponded to constraints that were equalities. And so if you look at the dual cheat sheet, if a constraint is an inequality, the variable in the dual has to be unrestricted. Okay, so we worked very hard. We started with this shortest path LP, and we got this shortest path dual. So now let's spend a little bit of time interpreting what this shortest path dual actually means. And we're going to do that in a couple of ways. So first we're going to do it algebraically, and then we're going to just think about it a little bit and see if we can come up with some meanings to what all of these variables mean. So this was our shortest path dual. So to start thinking about it algebraically, consider the following. So just consider a vector pi 0, pi 1, pi 2, all the way up to pi n. So this is just giving us values of all the variables that are in this program. Let's say it is feasible and has an objective function value of f. So in other words, when I take pi s and subtract it from pi t, given all these values, I get out some number like 5, but we're just going to call that number f. Now, let's shift the entire vector by a constant. So in other words, what we're going to do is we're going to take this vector, and to each coordinate we're going to add the same constant. So let's think about this new vector and what kind of an objective function value it would have. Well, this new vector, when I plug in here, the new value that it has for pi s would be whatever the old value was, but added with b. And its new value for pi t is going to be whatever the old value for pi t was, but added with b. And when we do that, these b's are going to cancel, because I get a minus b from this side and a plus b from that side. And then I'm going to end up with whatever the original value was. So this vector here has an objective function value of f also. So in other words, shifting everything by a constant kept the objective function to be exactly equal to whatever the original value was. Okay, so is this vector feasible? So let's think about if this particular vector is feasible when we plug it in here. So when we plug it in here, on the left-hand side of these inequalities, we're going to have the b's cancel out again. And we know that the original vector was feasible, so that means that the shifted vector must also be feasible. So is also feasible. because the original unshifted vector was feasible. So that means that there's kind of a extra degree of freedom in this linear program. If you give me any vector for the linear program, I can start shifting it by a constant in any direction, and I'm going to keep the same objective function value, and it's still going to be feasible. And so what we're going to do here is we're going to get rid of this extra degree of freedom by basically taking this linear program and in it we're just going to throw in the constraint pi s equals 0. So when we add this constraint pi s equals 0, now we can no longer do this shifting because we took one coordinate and we just fixed it to be 0. And we could have done this with any coordinate. We could have said pi t equals 0 or pi t equals 5 or whatever we wanted. But we just said pi s equals 0. And that's one way of getting rid of this, this shifting degree of freedom. So of course, whenever I set pi s equals 0, that thing immediately allows me to drop pi s from the objective function here because I know that's 0. So now the objective function is just maximize pi t subject to all of these things. Okay, so that was just an algebraic way of looking at the resulting linear program. But let's now spend a little bit of time to try to think about what these pi variables might actually mean. And to do that, let's consider a particular small example here. So let's think about this, this graph. So s goes to 1, which goes to 2, which then goes to t. So we have a pi t over here, we have a pi 2, a pi 1, and a pi s. And each of these edges has some length on it. So this is cs1, c12, and this is c1t, or c2t, is the length on that edge. Now, this linear program is asking us to make pi t be as big as we can possibly get it to be. And so we'd really like to make it infinity, but we can't make it infinity because pi t is involved in some of these constraints over here. And in particularly, it's involved in only one constraint, and that constraint comes from this edge right there. So let's write down what the constraint looks like. It looks like something like minus pi 2 plus pi t less than or equal to c2t. So that's the constraint that comes out of that edge. Or rewriting it, we could say that pi t is less than or equal to c2t plus pi 2. So if we want to make pi t be as big as possible, that means that we should be trying to make pi 2 also be as big as possible. Because the bigger we can make pi 2, that allows us to make pi t bigger. So if we want to make pi 2 as big as possible, the thing that's going to stop us from doing that is a constraint that comes from this edge. And that constraint is going to look something like pi 2 less than or equal to c12 plus pi 1. And that's really comes from the same kind of rewrite as we did originally here. And again, if we want to make pi 2 as big as possible, that means we want to make pi 1 as big as possible. But there's something that's restricting us from making pi 1 as big as possible, and that's the constraint that comes from this third edge. And the third edge says that pi 1 has to be less than or equal to cs1 plus pi s. But we know that pi s is 0 because that's the extra constraint that we added to the linear program here. So we can just drop that with 0, which says that pi 1 has to be less than or equal to CS1. So that's the biggest we can make pi 1, which tells us that we can make pi 2 be as big as C12 plus CS1, because that was the biggest that we can make pi 1, which in turn tells us that pi t could be as big as CS1 plus C12 plus C2t. And now the key here is to realize that this sum right here is the distance from S to T. And this sum right here, that was as big as we could make pi 2, this is the distance from S to 2. And similarly, that's the distance from S to 1. And so that's giving us an interpretation of what these pi values mean. So these pi values for nodes on the shortest path from S to T, the pi values give the distance of the node away from S. And that's exactly what happened here. Node 1 and node 2, they were on the shortest path from S to T, and so their pi values got set exactly to be equal to the distance of that node away from S. But it's possible that maybe we have node 3 that is not on the shortest path. So maybe this has 10,000 length right there, and then 10,000 length right there. So this pi 3 value for a node that's not on the shortest path, this value doesn't have to be the distance away from S. It turns out that there's some leeway on what setting you could give to that variable. It could be the distance away from S. That always works. But it could potentially be something else. So in general, the best kind of description of the shortest path dual that I've encountered is the following. So just imagine that the graph is represented by a ball of yarn that we've just tied together in the form of a graph. So every node is a knot, and every edge is represented by a piece of yarn that's as long as the edge is long. Then you can think of this shortest path dual as doing the following. We're taking out a ruler, and we're placing the ruler here on the table. And we're taking the knot for pi s. We're taking the knot for S, and we're placing that at 0. So that's happening with this extra equation that we threw in here, the pi s equals 0. So that tells us we're taking the knot for S and placing it at 0. The objective function, maximize pi t, what that's telling us is take the knot for node T and move it as far to the right as you possibly can. So move it as far down the ruler as you can. And of course, eventually, we're not going to be able to move it any farther to the right because all the yarn is going to get pulled tight. And what's going to happen when it gets pulled tight is that the shortest path from S to T is going to get pulled to be exactly parallel to this ruler. So these are going to be all the nodes on the shortest path from S to T. And so you can see now how for those nodes that are on the shortest path, their pi values are going to be exactly the distance away from S, and pi t is going to be the distance that t is away from S. But if I had a few other nodes here that are not on the shortest path, they could potentially be kind of hanging loosely down here off of this taut graph. And so there is some leeway on what we can set their pi values to. And that leeway corresponds to our ability to kind of move this knot up and down the ruler, having fixed the locations of the knots for node S and node T. But it's always possible for us to take this knot and move it to the rightmost that we can. And then what we're doing is basically setting the pi value to be equal to the distance of that node away from S. So that's a basic interpretation of the shortest path dual. It's just the pi values are giving us distances away from S. But we started out class not so much talking about shortest path duals, but talking about shortest path interdiction. So let's go back and see what happened in terms of the shortest path interdiction. So this dual here was inside. It was inside of a maximization. So we took the dual of this inner problem, but the outside problem is still there. So maximize over x and some resource constraints on x. So these are the resource constraints on x. And then these x's appeared over here as coefficients of the y variables. So when we took the dual, these coefficients in front of the y variables ended up on the right-hand side. So over here, we should really have a plus dij xij, because this entire thing was the coefficient of the y variable before taking the dual. And so now we're pretty happy because both the x variables and the pi variables are doing the same thing. They're both trying to maximize. So we can now take this problem and stick it into GAMS or into Cplex to try to figure out what are the best locations to attack. But this actually helped with another problem. So we also had this problem of that the formulation we began class with was not a linear program. But the result that we have here is a linear program because we don't have any sort of cross multiplications between pi variables and x variables. So everything here, in some sense, works just fine. So we can take it and stick it into a mixed integer linear programming solver, and it should be able to spit out an answer for us in terms of what are the best edges to look at for doing some kind of an attack on a particular shortest path operator. But let's talk about efficiency for a second. So if we go off and we put this into Cplex, what Cplex is going to do to try to solve this is branch and bound. And let's just recall how branch and bound works. So the branch part is that it's going to take all of the solution space and split it into a couple of sections. So maybe here it sets x naught equal to 1. And over here it sets x naught equal to 0. So it's going to branch on one of these binary variables. So remember that all these xij's are in 0, 1. So here it's branching on a particular binary variable. And then for each side of the solution space, it's going to try to get an upper bound and a lower bound. So splitting the solution space is the branch part, and finding these upper and lower bounds is the bound part of branch and bound. So for our particular problem, what we're trying to do is we're trying to maximize. And since we're maximizing, the way that we can find these upper bounds is through an LP relaxation. So what I mean here is that over here we fixed one variable, we've given it a value, but we have a whole bunch of other binary variables. And to get an upper bound, what we're going to do is we're going to take those integer binary constraints and we're just going to replace them with something like xij is less than or equal to 1 and bigger than or equal to 0. So this new constraint that we've added is less restrictive than the original one. So that means that we can only possibly get a better answer with this less restrictive constraint. So that's why that gives us an upper bound. And so we're going to do that for both sides here. For a lower bound, you can get a lower bound from any feasible integer solution with x not equal 1. And here is from any integer feasible solution with x not equal 0. So the reason that these give lower bounds is because the optimization problem is looking for the best integer feasible solution. So that means if I take a look at any integer feasible solution, well, the best one must only possibly do better than that. So that's why any particular feasible integer solution gives you a lower bound. So now we've branched and we've bound, but the reason that we do branch and bound in the first place is that we're hoping for some cancellations. So we're hoping that we can drop one of these two sides. But we can only do that if one of these lower bounds is bigger than an upper bound. So if one lower bound is bigger than the upper bound, of the other side, then we can drop the side with the poor upper bound. So in other words, if this lower bound is bigger than that upper bound, we know that an optimal solution cannot possibly come from here. And so we'll just drop this whole side, this whole part of the solution space. We'll never look in here again. And so we're hoping that by doing pruning like this, it's going to stop us from having to explore the entire solution space. But if it ever happens that we're getting very poor upper and lower bounds, if somehow these two things are poor, then we're never going to get this kind of cancellation and this pruning, and branch and bound is going to take forever. And that's exactly what happens on problems like this. It turns out that branch and bound is not quite as efficient as we'd like it to be, and it's because these upper bounds from the LP relaxation end up being very, very big. They end up being gigantic. So let me give you an example of why that is. So let's consider a particular graph here. I have two nodes S and T, and I have 3 bridges between them. So let's say the costs over here are 0. The costs on these bridges are 1. And we can choose which bridge to attack. So we have 3 attack variables, x0, x1, and x2. But we want x0 plus x1 plus x2 to be less than or equal to 1. And we want all 3 of them to be binary. So in other words, we're saying you can only attack one of these bridges. So in addition to saying that you can only attack one, I have to tell you how effective it is. So let's let Dij, which is how much longer the arc is if we attack it, for all three attacks, be, let's say, 30. So in other words, if you attack this bridge, what you're going to do is you're going to effectively increase its distance by 30. So its distance would used to be 1, and after you attack it, its distance would be 31. So for the integer program, the one where we actually have these integer constraints on the x's, the optimal solution, pretty much regardless of where you choose or which bridge you choose to attack, the operator is just going to walk around your attack. It's going to take one of the other two bridges. And so the optimal value here is 1, because regardless of what you do, you can't stop the operator from finding a shortest path of 1. But the LP relaxation, so that's when we drop this integer constraint and we just say that the xi's have to be between 1 and 0. This LP relaxation, what it's going to do is it's going to set each of these x's to be equal to a third. So if we set each of them equal to a third, what that's going to do is it's going to increase the distance of each of these three edges from 1 to 11. And I got 11 by basically saying, well, 1/3 times this 30 gives me 10, plus the original distance of 1 gives me 11. So the LP relaxation, its optimal value, is going to be 11. And so from this example, you can see that the LP relaxation is going to give us just huge upper bounds. And since these upper bounds are so big, not very much pruning actually happens during branch and bound, which basically makes these problems kind of too computationally intensive and too difficult to solve just using straight branch and bound. And so next time, we're going to discuss some other methods of trying to go about solving these problems. And in fact, those other methods are going to provide us with something else, which is right now, we're in all of our formulations today, we're still solving shortest path using a linear program. But we know that Dijkstra's algorithm is much, much faster. So in the new method that we'll talk about next time, you'll see that we'll be able to bring back Dijkstra's algorithm and at the same time be able to get rid of this problem of huge upper bounds. And again, these huge upper bounds come from the fact that when you do the LP relaxation, what the LP relaxation is going to do is take your attack budget and just smear it out all over the whole graph. So it's just going to say partially attack every single edge. Of course, we're not able to actually do that. And that's what gives the disconnect between the LP relaxation and the real problem. But okay, that concludes lecture for today. Thanks a lot for listening, and I'll see you all next time.